Learning objectives. At the end of this topic, you will be able to describe the construction and working of an electric motor, explain the process of electromagnetic induction, describe the construction and working of an electric generator, discuss about various domestic electric circuits. Introduction. Rita and her friend Sheila.
I've heard about various domestic electric circuits. Can you explain about some of them in detail? Sure, let me tell you about it.
Electric motor. An electric motor is a rotating device that converts electrical energy to mechanical energy. Electric motor is used as an important component in electric fans, refrigerators, mixers, washing machines, computers, MP3 players, etc. Let's know how an electric motor works. An electric motor consists of a rectangular coil ABCD of insulated copper wire. The coil is placed between the two poles of a magnetic field such that the arm AB and CD are perpendicular to the direction of the magnetic field. The ends of the coil are connected to the two halves P and Q of a split ring. The inner sides of these halves are insulated and attached to an axle. The external conducting edges of P and Q touch two conducting stationary brushes, X and Y respectively. Current in the coil ABCD enters from the source battery through conducting brush X and flows back to the battery through brush Y. Notice that the current in arm AB of the coil flows from A to B. In arm CD, it flows from C to D, that is, opposite to the direction of current through the arm AB. On applying Fleming's left-hand rule for the direction of force on current-carrying conductor in a magnetic field, we find that the force acting on arm AB pushes it downwards, while the force acting on arm CD pushes it upwards. Thus, the coil and the axle O, mounted free to turn about an axis, rotate anti-clockwise. At half rotation, Q makes contact with the brush X and P with the brush Y. Therefore, the current in the coil gets reversed and flows along the path DCBA. A device that reverses the direction of the flow of current through a circuit is called a commutator. In electric motors, the split ring acts as a commutator. The reversal of current also reverses the direction of force acting on the two arms AB and CD. Thus, the arm AB of the coil that was earlier pushed down is now pushed up, and the arm CD previously pushed up is now pushed down. Therefore, the coil and the axle rotate half a turn more in the same direction. The reversing of the current is repeated at each half rotation, giving rise to a continuous rotation of the coil and to the axle. The commercial motors use 1. An electromagnet in place of permanent magnet. 2. Large number of turns of the conducting wire in the current-carrying coil. And 3. A soft iron core on which the coil is wound. The soft iron core on which the coil is wound, plus the coils, is called an armature. This enhances the power of the motor. Electromagnetic induction. When a current-carrying conductor is placed in a magnetic field such that the direction of current is perpendicular to the magnetic field, it experiences a force. This force causes the conductor to move. This was first studied by English physicist Michael Faraday. In 1831, Faraday made an important breakthrough by discovering how a moving magnet can be used to generate electric currents. To observe this effect, let's perform the following activity. Take a coil of wire AB having a large number of turns. Connect the ends of the coil to a galvanometer as shown. Take a strong bar magnet and move its north pole towards the end B of the coil. We can observe that there is a momentary deflection in the needle of the galvanometer, say to the right. This indicates the presence of a current in the coil AB. The deflection becomes zero the moment the motion of the magnet stops. Now withdraw the north pole of the magnet away from the coil. Now the galvanometer is deflected towards the left, showing that the current is now set up in the direction opposite to the first. Place the magnet stationary at a point near to the coil, keeping its north pole towards the end B of the coil. We see that the galvanometer needle deflects towards the right when the coil is moved towards the north pole of the magnet. Similarly, the needle moves towards the left when the coil is moved away. When the coil is kept stationary with respect to the magnet, the deflection of the galvanometer drops to zero. Let's now perform a variation of the activity in which the moving magnet is replaced by a current-carrying coil, and the current in the coil can be varied. Take two different coils of copper wire having a large number of turns. Insert them over a non-conducting cylindrical roll as shown. Connect the coil 1, having larger number of turns, in series with a battery and a plug key. Also connect the other coil 2 with a galvanometer as shown. Plug in the key. You will observe that the needle of the galvanometer instantly jumps to one side and just as quickly returns to zero, indicating a momentary current in coil 2. Disconnect coil 1 from the battery. You will observe that the needle momentarily moves, but to the opposite side. It means that now the current flows in the opposite direction in coil 2. In this activity, we observe as soon as the current in coil 1 reaches either a steady value or zero, the galvanometer in coil 2 shows no deflection. From these observations, we conclude that a potential difference is induced in the coil 2 whenever the electric current through the coil 1 is changing, starting or stopping. Coil 1 is called the primary coil and coil 2 is called the secondary coil. As the current in the first coil changes, the magnetic field associated with it also changes. Thus, the magnetic field lines around the secondary coil also change. Hence, the change in magnetic field lines associated with the secondary coil is the cause of induced electric current in it. This process by which a changing magnetic field in a conductor induces a current in another conductor is called electromagnetic induction. In practice, we can induce current in a coil either by moving it in a magnetic field or by changing the magnetic field around it. It's convenient in most situations to move the coil in a magnetic field. The induced current is found to be the highest when the direction of motion of the coil is at right angles to the magnetic field. In this situation, we can use a simple rule to know the direction of the induced current. Stretch the thumb, forefinger, and middle finger of the right hand so that they're perpendicular to each other. If the forefinger indicates the direction of the magnetic field and the thumb shows the direction of motion of conductor, then the middle finger will show the direction of the induced current. This simple rule is called Fleming's right-hand rule. Electric generator. Based on the phenomenon of electromagnetic induction, the experiments studied above generate induced current, which is usually very small. This principle is also employed to produce large currents for use in homes and industry. In an electric generator, mechanical energy is used to rotate a conductor in a magnetic field to produce electricity. An electric generator consists of a rotating rectangular coil ABCD placed between the two poles of a permanent magnet. The two ends of this coil are connected to the two rings R1 and R2. The inner side of these rings is made insulated. The two conducting stationary brushes, B1 and B2, are kept pressed separately on the rings R1 and R2 respectively. The two rings R1 and R2 are internally attached to an axle. The axle may be mechanically rotated from outside to rotate the coil inside the magnetic field. Outer ends of the two brushes are connected to the galvanometer to show the flow of current in the given external circuit. When the axle attached to the two rings is rotated such that the arm AB moves up and the arm CD moves down in the magnetic field produced by the permanent magnet. Let us say the coil ABCD is rotated clockwise. By applying Fleming's right-hand rule, the induced currents are set up in these arms along the directions AB and CD. If there are a larger number of turns in the coil, the current generated in each turn adds up to give a large current through the coil. This means that the current in the external circuit flows from B2 to B1. After half a rotation, arm CD starts moving up and arm AB starts moving down. As a result, the directions of the induced currents in both the arms change, giving rise to the net induced current in the direction dCBA. The current in the external circuit now flows from B1 to B2. Thus, after every half rotation, the polarity of the current in the respective arms change. Such a current, which changes direction after equal intervals of time, is called an alternating current, abbreviated as AC. This device is called an AC generator. To get a direct current, a split-ring type commutator must be used. With this arrangement, one brush is at all times in contact with the arm moving up in the field, while the other is in contact with the arm moving down. We have seen the working of a split-ring commutator in the case of an electric motor. Thus, a unidirectional current is produced. The generator is thus called a DC generator. The difference between the direct and alternating currents is that the direct current always flows in one direction, whereas the alternating current reverses its direction periodically. Most power stations constructed these days produce AC. Domestic electric circuits. In our homes, we receive supply of electric power through a mains supply, also called the mains, either supported through overhead electric poles or by underground cables. One of the wires in this supply, usually with red insulation cover, is called the live wire or positive. Another wire with black insulation is called the neutral wire or negative. In our country, the potential difference between the two is 220 volts. At the meter board in the house, these wires pass into an electricity meter through a main fuse. Through the main switch, they are connected to the line wires in the house. These wires supply electricity to separate circuits within the house. Often, two separate circuits are used, one of 15 ampere current rating for appliances with higher power ratings, such as geysers, air coolers, etc. The other circuit of 5 amp current rating for bulbs, fans, etc. The earth wire, which has insulation of green color, is usually connected to a metal plate deep in the earth near the house. This is used as a safety measure, especially for those appliances that have a metallic body, for example, electric press, toaster, table fan, refrigerator, etc. The metallic body is connected to the earth wire, which provides a low resistance conducting path for the current. Thus, it ensures that any leakage of current to the metallic body of the appliance keeps its potential to that of the earth, and the user may not get a severe electric shock. In each separate circuit, different appliances can be connected across the live and neutral wires. Each appliance has a separate switch to on or off the flow of current through it. In order that each appliance has equal potential difference, they are connected parallel to each other. Electric fuse is an important component of all domestic circuits. A fuse in a circuit prevents damage to the appliances and the circuit due to overloading. Overloading can occur when the live wire and the neutral wire come into direct contact. In such a situation, the current in the circuit abruptly increases. This is called short-circuiting. The use of an electric fuse prevents the electric circuit and the appliance from a possible damage by stopping the flow of unduly high electric current. The joule heating that takes place in the fuse melts it to break the electric circuit. Overloading can also occur due to accidental hike in the supply voltage. Sometimes, overloading is caused by connecting too many appliances to a single socket. Summary. Let's summarize the topic. Electric motor is an important component in electronic devices. An electric generator uses mechanical energy to rotate a conductor in a magnetic field to produce electricity. A fuse in a circuit prevents damage to the appliances and the circuit due to overloading. Wires pass into an electricity meter through a main fuse.